Um, my name is Naveen Swami. I'm a software developer at Amazon. I work on deep learning frameworks and tools, specifically Apache MXNet. Today, I want to talk about a little bit about deep learning, then the Apache MXNet deep learning framework. Finally, the topic of today, distributed inference, the challenges in it, how to use MXNet and Spark together to solve those problems. How many of you know what deep learning is here? I don't want to waste your time. If you already know, I can skip through. And OK, let me just quickly go through them. So like you all know, machine learning is about using algorithms to process data and make decisions. But in traditional ML, before you could use an algorithm, you had to go do feature extraction, where you told the algorithm what are the salient features in your data to look at before you could use. This had some drawbacks. Specifically, it needed domain experts. If you're doing recommendation systems on retail products, you needed a domain expert who understands what are the features in it. And then these were handcrafted features, so they were error-prone. And most importantly, this doesn't work on new problems. You need to start over all again. Deep learning or neural networks solves this problem differently. The term deep learning and neural networks is used interchangeably. So the area of neural network design originally was inspired by how learning works in our brain. But today, it's become more of an engineering and algorithmic challenge to solve various machine learning tasks. In this system, it learns the most important features from experience itself by building hierarchy of concepts, learning each concept at a time. Take this example, which is a neural network which has many layers. And here, we are trying to feed an image and classify or categorize into 3 different categories: car, person, and dog. So the first layer is called the input layer, where you feed the raw pixels to the network. And then you have a hidden layer, the first hidden layer, which is trying to make sense of edges in the image. The layers in between input and output are called hidden layers because the values are not given by the data. The system is learning to represent the relationship between the input and output. And then you have a second hidden layer that's trying to make sense of corners and contours. You have a third layer, which is identifying object parts in the image. Finally, you have an output layer giving you probabilities across these 3 categories. Once we train it well, if you feed an image of a dog, you should get a high probability on dog, the category dog. One thing to note, deep learning, here the word deep doesn't mean it's gaining deeper understanding. It just means that the number of layers is really, really large. So deep learning dates back to 1940s. A few things happened that changed the landscape in the last 5 to 10 years. One of them was availability of data. With digitization of everyday life and commoditization of IT resources by cloud providers like AWS, it's never been easy to collect and analyze data, right? So with lots and lots of data, we are able to create deeper and deeper networks that's learning a lot more concepts in the data. And then you have high-performance compute. Here I mean GPUs. General-purpose CPUs have a few cores that can support only a fewer number of software threads, while GPUs have hundreds of cores that supports thousands of cores, thousands of threads. This is especially important for deep learning because if you look deep down in the neural networks, these are all linear algebraic operations that can be heavily parallelized. So with GPUs, we can get faster experiments and faster learning. In 2009, researchers started using GPUs, and suddenly they were able to create models that were 10 to 20 times bigger and learn much faster. Another thing is that this field is rapidly changing. You see papers coming out every day, algorithmic advances. So that definitely helps to faster learning and get better accuracy. In that respect, in 2012, Alex Krevesky from Jeffrey Hinton's lab, he is a pioneer in the area of AI and works out of Canada. He presented a model based on deep neural networks for image classification, where the task is to identify the most significant object in the image, which was like 30% more accurate than the best known algorithms to that date. This was in 2012, and a lot more advances have happened after that. All of this gives us bigger and better models with better AI, giving us better AI products that's permeating into our everyday life, like in personal assistants, in machine translation apps, autonomous vehicles. This might not be very useful here, but with such great public transport, I come from San Francisco Bay Area. It's horrible. My commute is 1 hour each way, and I would love to see an affordable self-driving car. I'm really excited and waiting for it. And then there are companies that are taking into deep learning into healthcare field. This one in particular is trying to help physicians diagnose heart diseases and avoid unnecessary angiograms. And then there is AlphaGo Zero. This system learned the world's greatest intellectual game, Go, just by playing against itself without needing any expert data. Just to give you a perspective on the complexity, the number of configurations on a Go board is more than the number of atoms in the universe. That's 10 to the power 78. And it ended up winning against the world's Go champion, KJ, just by playing itself against itself. One thing to note, without any panic, is that the system still had to go play millions of times before it could master, while players themselves played much fewer number of times, and they start playing instinctively. So we are still relevant. Machines have not taken over us. So let's see where deep learning falls in this broad category.
Sorry, maybe it's not like a relevant question. But you say they had to play. Hello. The machine had to play millions of times, but how fast they had to play it? Like in a shorter time than a human being?
No, it took a couple of days or weeks. I don't know the exact number, but it's not really. Yeah, you're right that you can power up, compute, and feed it, but to solve problems, you need much more than just being able to play it so many times, right? Yeah. So let's see where deep learning falls into this broad category of artificial intelligence, which was meant to actually focus on developing cognitive capabilities of humans to reason and think. Over many years, many machine learning and non-machine learning models, methods have been developed and tried to achieve AI. In particular, in non-machine learning methods, there was rule-based system where they believed that they could achieve true AI just by handcrafting rules. One popular one was called expert systems in 1950s. And then machine learning, it's an algorithmic field that blends ideas from computer science, statistics, and many other disciplines to solve problems that are harder for humans, but easier for machines, and then which could be expressed as formal mathematical rules. Deep learning is a subset of machine learning, which tries to solve problems that are easier for humans to solve intuitively, but harder to express problems in terms of mathematical rules. Whether deep learning is trying to achieve true AI is really debatable. And I was reading an article by Michael Jordan on AI revolution. He's a computer science professor and statistician in UC Berkeley. He had a very interesting take on it. He goes on to say that what we have developed and focusing are actually to develop intelligence augmentation systems, IA, not AI, to help human intelligence and creativity. That was interesting. Despite all the progress, there are some limitations to deep learning. One of them is that it requires lots and lots of data, correspondingly lots of compute power. Though we have lots of data, to get expert data, it's very expensive and unreliable, sometimes just not available. And then it cannot detect inherent bias in data. Imagine deploying these decision-making systems at large scale. If it was trained on data that has bias, that's a disaster awaiting, right? So, and another thing is that sometimes you cannot explain why some models work and some don't. Often, the application scientists say that there is a black art of hyperparameter tuning involved in deep learning to understand or to make it work, and then you can only hypothesize after the fact. Hopefully, you're convinced that deep learning is a big deal. Let's see how it works. It has two phases. One is training, where you develop a model and feed lots of data, and then at the end, you check if it met your output objective. If not, we send the error back. Let's take this very dummy network where it has an input layer with 2 inputs and a hidden layer and an output. First, we pass samples from a data set. This is also called forward propagation. The layers are connected in between with weights, which are initialized randomly to start with. And then we define our objective function. Here, for illustration, it's very simple. Y equal to 1.0 is what I want. And if it doesn't meet, we take a loss function and propagate the error back, updating the weights by taking gradients of each of the weights. This is where the learning happens. We do this many, many times until the objective is met or the desired accuracy is met, at which point in time it gives us a model, also called a pre-trained model. Next, making use of this pre-trained model in your real-life applications is what deep learning inference is. We take the model and feed new application data to get predictions. This is just running half of the training where we run only the forward pass. Deep learning inference can be done in 2 modes. One is real-time, where you need immediate feedback, for example, in fraud detection. And then you can do it in batch mode when you have lots and lots of data. This is especially helpful when pre-computations are necessary for services that are like recommender systems, which has to go sort and rank against hundreds of user products. Another place where it's useful is to, let's say, you have already a model that's been used to run inference on, and now you develop a state-of-the-art model. You want to go backfill all of those inferences. So we can use batch mode there. And another one is if you develop new models, before you can deploy it to production, you want to test it on your existing data to verify if it is giving you a better result. Let's take a look at the types of learning in play today in deep learning. The first one is supervised learning, which is where a lot of advances have been made. This is telling the system what semantic content is present in your data, and it has to match that and learn the weights to actually match the output. Example is if you feed for image classification an image of a dog, you tell the system, hey, the output I'm expecting here is a dog. This is used in speech recognition, machine translation, and like I said, image classification. And then another type of learning is unsupervised learning. Like I said, there's lots of data, but we want to find patterns in that data. We use unsupervised learning to do, for example, clustering and association discovery. Then there is another new exciting type of learning, which is in between supervised and unsupervised, where it tries to identify the patterns, but when it cannot understand what's in the data, it queries a human, queries a user to get the labels and continue from there on. And there is also reinforcement learning, that is learning in its current environment from the experiences using rewards and feedback. For example, robotics is one that makes use of deep reinforcement learning. So far, we covered a few things about deep learning. So let's see Apache MXNet framework, which is an incubating project at Apache. The first question is, why MXNet and how is it so different? I have many reasons here. One is it offers programming APIs in many different languages, so you don't have to learn another language to use this. It also offers simple syntax, and it supports both imperative and declarative style. So as we speak, there is a contributor who is working on a Clojure API. If there are any Clojure interested, Clojure skilled audience here, you can use that. And next is that you can create highly optimized models that you can deploy to mobile and IoT. It's also very high performant. In training, we have seen that it can achieve near linear scaling across hundreds of GPUs. And again, open source incubating, it's truly open source because no one entity can control the project. Right, so anybody is welcome to contribute to this cause. Then there is Onyx support. How many of you know what Onyx is? There are many awesome deep learning frameworks, but once you start using them, all your intellectual property is embedded in the model that it creates. Now you're stuck to the framework. If you want to move to another framework, there were no options. So this is an open source initiative by Amazon, Microsoft, and Facebook to come up with an interchangeable model format. So you can do training on one deep learning framework like PyTorch and bring it onto MXNet and run them here. And then there's Gluon support. Gluon is another open source initiative to simplify and standardize the deep learning APIs. It's led by Amazon and Microsoft. This offers imperative APIs that is easy to understand, easy to use. MXNet not only implements these APIs, it also on the back end transforms into a highly efficient symbolic graph. So now you not only can go quickly prototype your model, you can also deploy it to production without losing any performance. Let's look at a few constructs in MXNet. The first one is NDArray. It's nothing but a multi-dimensional array. So this supports imperative tensor operations that work on CPU and GPU. Tensor is used interchangeably with multi-dimensional array, but if mathematicians hear me say that, they get very upset. Tensors are much more than multi-dimensional array, which represents relationships of data at a higher dimension. Anyway, there's then a symbolic APIs. It is similar to NDArray, but adopts declarative programming for optimization reasons, where you create the graph first and then give it to the system to optimize it. In this example, here we have two operations, simple, C equal to B star A and D equal to C star 1. If you used NDArray, the numerical computation would happen as it sees the statements or the operations. In symbolic world, you would first create a graph and then compile, at which point in time MXNet backend goes and optimizes, decomposes the operators and optimizes, removing all the redundant memory references and also parallelizing independent operations. In this example, you can see that C is not being used, so it optimizes to remove that redundant reference. Now we have lesser memory consumption. There's another set of APIs called module, which is designed to be high-level APIs to work with symbol. Module represents computational components that execute forward and backward pass on the network, and also it updates the parameters, which are the weights. With these APIs, you first create a graph of the network. In this example, we have two fully connected networks. Fully connected is something that has straight connections, and there are other types of network called convolutional RNN. So without going into the details, this creates a network, and then we feed it to the module, And the next step, we will bind this so that the backend will allocate memory for it. We'll bind with the input data shapes. Finally, we'll pass data to the module and call either the fit routine, which is to train the network on your data, or call the predict, which will, if you have a pre-trained model, will give you predictions on new application data that you have. Let's look at a small demo here. Here I'm showing MXNet is available as a Python pip package, so you can easily install it. And I'm showing you a ResNet 18. I will explain what ResNet 18 means in the next slide. And here there are two files, symbol and parameters. Symbol represents the network, and parameters are the weights in the system. If you look at the symbol, you see that it's made of many, many layers with convolution, pooling, and activation layers. And to the start of it, we will pass the data. There you go, over there. And if we and in the parameters, you'll see these are floating point values or doubles representing the weights between the layers. So there is another file called synset, which represents the relationship between categories and the labels. Let's look at a small example and see how to run prediction. Here I'm using an image of a ship to predict. It's a 3-dimensional array. Like I said, this means that it has 3 channels RGB. You can also check by running a shape operation on it. You see that it has 3 dimensions there, and the size is 32 cross 32. Once we run predict on it, you can see that it gives you, as a container ship, with about 59% accuracy, which isn't bad. You want more than that, obviously. So, so far I've covered a few concepts in deep learning and talked about MXNet. Now let's see the challenges in distributed inference. When you have a large data set to run inference on, you want to run them on multiple machines, right? There are a few challenges to efficiently running this. The first one is you need a high-performance deep learning framework. Just to give you an idea of the complexity involved, to run forward pass on one image, it takes about, on a model like ResNet, which I'll talk next, it takes billions of floating point operations. So your framework needs to be really efficient to make sure that your resources are well utilized. And since you have a lot of data, you need a distributed cluster that's able to do resource management very well, and then schedule jobs for you, track them, and if it fails, retry them. You need to also efficiently partition your data across the cluster so that all the resources are well utilized. You need a deep learning setup as well. Sometimes it can be very hard to make it efficiently work because of the dependencies involved. You need the right GPU drivers. You need the right libraries. So for this particular problem, Amazon Deep Learning Army, where you can launch a EC2 instance, and Amazon EMR makes it a breeze to use. Many of these look very familiar and similar to large-scale data processing systems, right? Apache Spark solves many of these problems, and you can use multiple cluster managers. It also works very well with MXNet, and it integrates with Hadoop and big data tools. If you have data on Hadoop clusters, now you can gain new insights using deep learning. So I have a demo. For this, I will be using ImageNet trained ResNet 18 classifier. ImageNet is a project that runs annual competitions for visual recognition tasks, and researchers worldwide compete there. And they have a database of 1 million images across 1,000 different categories. In 2015, Microsoft researchers presented a model that was able to surpass human capability in this narrow subset of visual recognition tasks. Originally, it had 152 layers. It's called residual neural networks. Here I'm using ResNet 18, which is the 18-layer version. Even this needs about 3 billion floating point operations. And for demo, I will use a C410 test dataset with 10,000 images. ImageNet is for research, so I couldn't use it here. I'm using a publicly available data set. I will use the Python version of Spark on Amazon EMR. If you're a Scala developer, MXNet is also available in Scala, so you can use that. And also, it's not necessary to use on EMR. You can have your own Spark cluster and have MXNet installed. Also, the demo is based on CPUs, but if you have lots of data, then you can easily extend this to GPUs. So let's see how the pipeline itself looks like. All of my images I put them in S3, but you can use HDFS or any highly available distributed file system, or even EFS for that matter. So I will download all the S3 keys on driver. There is no need to distribute or move images across driver to executor. How many of you know Spark? Okay. Yeah, it has a driver, and there are workers. Driver submits the job to the workers and manages the scheduling. So what I was saying is, you don't need to move data between these two components. All you can do is have the keys, create the key, just download the keys onto the driver. And in Spark, there is a term called RDD. You can create a RDD and then partition across the cluster. RDD is resilient distributed data set. So it's a very efficient way to distribute data. And on the executor, we will fetch a batch of images. Like I said, these are linear algebraic operations. A batch size of more than one is just another dimension in tensor. So we will try to parallelize that by fetching a batch of images. And then we'll decode this to NumPy is another library, Python library. We will convert that to NumPy format and run predictions using the MXNet library. All of this happens inside the Spark map partitions method. Spark has map. It's based on MapReduce, but it calls transformations and actions. And in the transformation, you can either act on one data item at a time or a chunk of data at a time. So what I did here is to take a chunk of data in map partitions and then convert it into a batch. Also, we don't want to initialize this model over and over for every map partition. So we want to make sure that adds to latency. So we will initialize that only once. I'll show you how. And finally, we will collect the predictions at the driver. If you look at just looking at the code, here I'm setting the number of executor cores. By default, Spark goes and creates one task per core. But MXNet uses all the CPUs very efficiently. So I'm asking Spark here to create only one task per executor and not compete with MXNet. So it just adds context switching. And like I said, I'm using map partitions. The number of partitions is based on the batch size and the number of images you have. Batch size is something that I determined by running experiments based on the CPU type I have and how much memory I have. Like I said before, we need to load the model only once. For whatever reason, Spark doesn't give you init routine on the executor. Instead, we use a singleton and a static method to load the model onto the process only once. And we have another thing is we don't need to, actually we have to only import the libraries at the map partition method instead of top of the module, because at that point PySpark just tries to serialize these libraries from driver to the worker and most often fails, saying this has pointer references which it cannot understand. So we'll import it at the map partition method and then make the libraries available on all the nodes. So it doesn't have to serialize. The libraries are already available. Let's just quickly see a small how to use it on EMR. It makes it very easy. It's a click of a button for you to install MXNet and Spark together. Here we don't need all those. I just need Spark, and we have MXNet 1.0 over there. And you just create a cluster. I will use a VPC, And let me show you that's for the core or the driver core node where the driver lives. And here we have GPU instances available if you want to make use of them. But here I'll just use a M3XL, which is enough for a data set that I have. And for core, I will use C4 8x large 4 such nodes. So yeah, and then you click a button and you'll just be able to create a cluster. Let's take a look at how to use this cluster. Here I take the master instance and then we'll log into that. Yeah, the code sample is available on GitHub, so I will try to clone that. I will clone that here and use that to submit a Spark job. Oops. All right. Okay, that exists already, so let's just submit the job. Okay, I have the command here on a blog that I wrote. I'll share it with you. Here I'm showing that we have 40 gigs of memory and 4 executors. I'm passing the model URLs and with a batch size of 64. You can also optionally pass a S3 bucket and a S3 key to write the output into. Here, that's the test bucket that I have, demo bucket. If you want to test drive this, you can use it. And we will give it a key to write the output. Okay, submit. Yeah, once it submits to the driver, we can go look at it on a resource manager URL that's available with Hadoop and Spark. It's submitting that job yet. All right, it started running. That's great. Let's take a look at the URL here. It shows you the job execution flow here. You can go to the application master. Here you see that it's already started. Let's see what's going on. It made about, let's see. Okay, it made about 165 partitions because it was 64 and had 10,000 images. Let's look at some logs to see what it's doing. You can see that it's loading, downloading the model, and it's created the symbol. And then you can see it ran a prediction on a batch of image. That's great. Let's quickly look at the job that's already run. Okay. This is a job I had previously submitted, and you can see that it was able to process 10,000 images in about 4 minutes. That was pretty impressive. To summarize, I talked about a few deep learning concepts and why deep learning is a big deal these days. Again, it's only a very tip of the iceberg. There's lots more. Next, I covered MXNet, NDArray, and symbol and module. Finally, we saw how to use MXNet and Spark for distributed inference. So for the project, we just released 1.2.0, and it has Scala inference APIs, a simplified set of APIs for Scala, and it's available on Maven as a Maven package. We're also working on Java APIs. We have heard that research scientists, while they prefer Python to model, but engineers want a type-safe language because they are putting it into production in a large system, and they're used to the ecosystem which has built around Java. So we are working on a simplified set of APIs in Java. We are also considering support of Spark data frames so that the communication becomes really smooth. Finally, this is our community is fast evolving, and I want to ask you to join hands to democratize AI, and it's an Apache project. The code is all available on GitHub, and deep learning is a very exciting field. Go check out, join us, and join our mailing list and see what's going on. Bring out your use cases so that we can prioritize them. There are some resources that I put together here. Apache/incubator MXNet on GitHub is our repo. I wrote a blog about it. it's available in the link. Then a few things. And if you're new to deep learning, MXNet Gluon has an excellent set of tutorials taking you from all the way from linear algebra and many basic concepts all the way to implementing papers, the latest, greatest papers. So check that out. And thank you so much for your patience. Yeah.
Yeah.